All right, we have seen the fundamental problem in AC to DC converter that we always encounter, namely the extinction angle and boundary points problem. So as I mentioned earlier, there are two major methods in numerical analysis for root finding, which is called the bracketing methods and the open methods. So in this video, I would like to focus on two methods, namely first the bisection methods and secondly the Newton-Raphson methods. So bisection method is categorized under the bracketing methods, in which we require a bracket in which the roots lies before we can begin with the algorithm. So let's get right away to the bisection method. So suppose that we are dealing with the finding the extinction angle, like the above problem. So in order to find beta, the extinction angle, we need to imagine that this curve is slightly extended until it crosses the horizontal axis, like we have here. So suppose that we know this root lies between a bracket, inside a bracket, in which the boundary of the brackets are A and B. So this is not a big problem because we know that beta in here lies between pi and 2 pi. So maybe we can say that A equals to pi, B equals to 2 pi. Or even we can assume that beta lies between pi and 1.5 pi or 3 pi over 2. So we can also say A equals to pi, B equals to 3 pi over 2 as the initial brackets. Okay, back to the problem. So now the algorithm for bisection method is first we have to find the middle points between A and B, in which we write C equals to A plus B over 2. So that means, the point C is the middle point between A and B. So let's say somewhere here, the middle point. So A plus B over 2 equals to C. Then we have to check the value of the function at each point A, B, C. So here is FA. And this one is FB. So before we proceed, I forgot to mention that how to know that a root lies between A and B is by multiplying the value of FA and FB. So since FA and FB are located on the opposite sides of the horizontal axis, so the multiplication between FA and FB is negative because FA in this case is positive and FB is negative. So if FA and FB have opposite signs, so the multiplication of FA and FB is negative, so we can conclude that there is a root lies between A and B. So back to the explanation. So now we examine what is the value of FC, the function when angle equals to C. So now the algorithm for bisection method is if FA times FC less than 0, we set the new boundary B equals to C. So, okay, in this regard, FA and FC, both of them are positive. So FA times FC is positive. So we cannot take this condition because it does not fulfill the algorithm that we have mentioned just now. Okay, second case, if FA times FC greater than 0, we set A equals to C. The new boundary C becomes the new boundary on the left-hand side, which is A. So this fulfills the condition of the second case. So now the new A is C, our C. So we update. It is like this point become the new A. And this is neglected. So now, as you can see, the bracket has been reduced. Previously, A and B is within this range, but now A and B has been reduced to this range only. And then we repeat the process. We repeat the algorithm. Find the midpoint between A and B. Now C is, let's say, somewhere here. Check FC. So FC is here. So find the multiplication between FA and FC. So now FA and FC in this case is negative because FA is on the top of the horizontal axis while FC is at the bottom. So if this condition fulfilled, we set B equals to C. The new boundary on the right hand side is C. So now we can remove this. So now this becomes the new B. So this is our B. And then this is FB. And then we repeat the process. Find the middle point again. As you can see now, the bracket has been reduced. And then let's say the middle point now between A and B is somewhere very close to XR, our desired root. So let's say this is the middle point C. Check C, which is somewhere here. So this is FC. So FC is negative. So FA times FC negative. So we set B equals to C. Now B move here. So this becomes the new B. And then repeat the process. Find the middle point again. Okay, and then this becomes the new A. And then finally the brackets become very tiny such that finally we can say that A is very close to C and very close to B. So if one of the FA, FC, or FB, very close to 0, we can conclude that one of them are the roots. Sorry, one of them is the roots. Okay, so that how we execute the algorithm for the bisection method. So again, bisection method require a bracket like A and B. Okay, the second method is called the Newton-Raphson method. So this is categorized as the open method, in which we does not require any brackets, but in fact we have to find any initial guess close to the roots. Okay, so the method is, first we need to find the differentiation of f at this point, at our initial point. So the differentiation is in fact the slope of this line that we call tangent at point x0. So the slope of f is written as f prime at x0 need to be found. So suppose that this line intersects the horizontal axis at point x1. So x0 is the initial guess, the initial points. x1 is the points where the tangents at point x0 intersect the horizontal axis. So now we have like a right triangle. So we know that the slope of the tangent, which is f prime x0, equals to the height of the sides, which is fx0, divided by the difference between x1 and x0. So x0 minus x1. So if we rearrange this equation such that I put x1 on my left-hand side, on the left-hand side of the equation, so I have s1 equals to x0 minus f x0 divided by f prime x0. And then I repeat the process. So now based on x1, we have to find, the value of the function at fx1, at x1. So again, we have to find the tangent line at point x1. So the line that intersects the horizontal axis, so we call this point as x2. So again, we have this right triangle. Let's choose other color. We have this right triangle, and then I can write the equation in a similar manner. F prime x1 equals to f x1 divided by x1 minus x2. So the slope of this line is f prime x1 because it is the tangent when x equals to x1. So I have this equation, I rearrange this, I get x2 equals to x1 minus f x1 divided by f prime x1. And then I repeat and repeat. So we can conclude that the algorithm for the Newton-Raphson is xi plus 1 equals to xi minus f xi divided by f prime xi. So this is the equation for the Newton-Raphson algorithm. It looks simpler than bisection, but the drawbacks of this method is we have to find the derivative of the functions. As an example, if I take this problem, the extinction angle problem, so if let me copy this. So in this regard, okay, if FB, now F beta is sine beta minus theta plus sine theta exponent negative beta over omega tau. So we have to find the derivative of f with respect to beta in order to fulfill the Newton-Raphson algorithm. So f prime beta is cos beta minus theta plus, since this is the constant, so just copy that. So the derivative of exponent power negative beta over omega tau is also exponent negative beta over omega tau, and multiply with the coefficient of beta, which is the 1 over omega tau and negative. So we get this kind of form for the differentiation of the function with respect to beta. So the algorithm for this particular problem can be written as beta I plus 1 equals to, beta I minus f beta I divided by f prime beta I. So we substitute this equation into here, and the second equation to the denominator.